Good afternoon and welcome to this bonus video on scheduling. Today what we're going to be doing is going through the slides in greater detail, starting with first come first serve and going through preemptive priority based scheduling. This will be to make up for going through these lectures a little bit fast in class. Here I'll be doing a deep dive and slow walk through each of these simpler scheduling styles. So we'll get started with first come first serve. Throughout this set I'll be using my grocery store analogy, probably because this is my preferred way to think about CPU scheduling. So first come first serve, this is like a typical grocery store line where we have everybody waiting their turn, and the process that's been waiting the longest, much like the person who waits the longest in a line, will be chosen to go next. And here in our analogy, when we choose a person to go next in the grocery store, they're going to be checking out at the till with the cashier. But in our computer, this is really a process that's going to be running on the CPU. And in our class, we're typically thinking about single CPU systems, unless we specify otherwise. So for this whole deck, we're going to be talking about single CPU systems. So there's only going to be one process running at a time. And here, when we say we choose a program that's been running, let me pull up my laser pointer, right? The program that's been ready to run the longest. What we're actually referring to here is our process states. So if you remember our process states, new processes get admitted to our system and they get placed in the ready queue. These ready processes will be managed by our scheduler. Our scheduler is the one who chooses which process gets to run next on the CPU. They make this transition, the scheduler dispatch transition. So when the scheduler decides it's a process's turn to run, they change their state. They do this scheduler dispatch. They select the process to go next, and it goes into the running state. So what we're talking about in this whole lecture is how do we go from ready to running? How do we manage our ready queue and choose the right process to run? And each of the algorithms, it's not letting me go back in the PowerPoint, but each of the scheduling algorithms we're going to study here, right, is going to be a strategy to choose which of the ready processes get to run next. So that's our goal today. And so the first example is first come first serve. We just say the process that's been ready for the longest gets to run next because they came first, so we should serve them first. It's just a simple line. And just to finish talking about this diagram, right, a running process can either terminate, which means that it doesn't have anything else to do. It no longer needs to run on the system, and it goes into this terminated state, waiting for its state to be collected by its calling process, or it can call an IO wait, right? So there's going to be a number of system calls that can be made that would cause the process to need to wait for some event. So if one of these events occur, go from running to waiting, they'll be put in some kind of a waiting queue associated to whatever event they're waiting for. And when it's no longer waiting, it'll be moved back into the ready queue. There's this final arrow, maybe the trickiest arrow on the diagram, right? This interrupt arrow up here. If we interrupt a running process, that means that we have something else we want to do. We're going to stop the process and transition its state back to ready. So a running process that gets transitioned back to ready, it still wants to run. It's ready to run. It isn't waiting for anything in particular, and it's not done. So this interrupt we're going to refer to as preemption in these slides, and that's particularly important, right? So when we have no preemption, what that means is the only way to leave the running state is to do so willingly by the process. So either that process is done or it needs to wait for something that hasn't happened. When we add preemption, that's adding this ability to interrupt the running process. So we're able to say, you know, I know you still want to run process, but actually we're going to transition you back to ready. So that's this interrupt arrow and how it influences our scheduling. All right, so let's get into it. Each of these examples, what I'm going to be doing is scheduling the same set of processes. We have P1 through 4 here with specific arrival and burst times. I'm going to have a screen that looks a lot like this. In the ready table, this is going to be our ready queue. We've got some kind of a structure right? That's similar to what we would have on our OS that will manage the processes that want to run, the processes that are in the ready state. So for our first example, when we do FIFO, this will just be a queue, right? This will be a queue of processes, and we'll keep track of some of their stats, whatever stats we need in order to run them. Then we'll have one process that can go into the running state. The reason why there's only one running process at a time is because we're on a single CPU system, right? So we only have one CPU, we can only run one process at a time. Then we have down here, we're going to be building out a schedule. Often when we ask you questions like this to prove your understanding, you're going to draw us a timeline that says when the process ran with the particular algorithm. So we're going to be building up a timeline, often referred to as like a Gantt chart or something. We're going to build out this timeline, and then using the timeline, we can calculate some statistics. These statistics are going to tell us, they're metrics, they're going to tell us how well our each algorithm did. I can't remember if I left the statistics into the slide deck. If they're there, we'll talk about them. If not, you can refer to the actual lectures if you want help doing the metrics again. All right, so let's get into it. Let's do our first example. So maybe I didn't mention, but here we have the arrival times and the burst times. So an arrival time just says, when does this process arrive to the ready queue? All right, whereas the burst time says, how long does this process need on the CPU before it changes state to something else, right? And that can be terminated or it can go to waiting. It doesn't really matter for these examples. So we'll just give you the time it takes for their next CPU burst and the time that they arrive in the ready queue, the time that their state changes to ready. And so maybe one important thing to point out before we get into it is these burst times. These are not a practical thing that we know. Processes don't arrive and tell us, hey, I want to run for 7 time units. When we're actually scheduling, we don't typically know these. But anyway, we talked about that in class. So I'll just focus on this example. So we start and our clock is at 0, right? So we're at time 0, and what we're doing is we're looking at how these processes are going to be scheduled. So at time 0, we see we have one process arrive, that's P1. So P1 enters our ready queue, it's ready to run. And because there's nothing else here, right? Nothing's running right now. We're not going to have a process in our ready queue and nothing scheduled. That doesn't make sense. So we schedule P1 right away. We say, okay, P1, at time 0, you're going to be the process that's running. And we keep track of some stuff about P1 here because it'll be helpful for other scheduling algorithms. Now, it's important to note, first come, first serve is not preemptive. Right, so first come, first serve is not preemptive, which means that when a process starts running, it's going to run for its full burst time before it finishes. It's going to use its full burst time and then leave the CPU. Right, we'll never have P1 getting interrupted. There will be no preempting P1. Okay, great. So P1, it's going to run from 0 to 1. We can see it updated in our schedule down here. We see it has 6 time units left. And there's nothing else to do on our system right now. Interestingly, what's going to happen at the next time unit is we're going to have our first change. This is going to be P2 arriving, right? P2 arrives at the next time unit, so we see it show up in the ready queue, right? P2 shows up in the ready queue, which means that it's going to take its place in line, right? We're at a grocery store. P1's still checking out its items. It's got 5 items to go, or in the actual case, right, we're saying 5 time units, whatever time units we're using, left to run. So it's going to continue running on the CPU or checking out its items, and P2's taken the first place in line. So this will keep running. P3, nothing particularly interesting happens other than P1's remaining time goes down. We're still running P1, so we see it as our running process in our schedule down here. At time P4, you should note that P3 will arrive. So we see P3 here is arriving. And then time 5, we have P4 arrive. But because this is non-preemptive, nothing can stop P1 from running, so P1's just going to keep running until its time is done. Now we see P1's remaining time is 0. It's ran for its 7 units, right? So it met its burst time. So it went from time 0 until the end of time 6. So then at time 7, we're going to see a transition from P1 to some new process, right? So P1 ran from 0 to 7, and then at 7, some new process started. So we look into our ready queue to choose which process gets to go next, right? And this is our scheduler now. Our scheduler gets to decide which of these processes it wants to run. And we said, in this case, we're scheduling with first come, first serve. So first come, first serve is going to pick the process that's been waiting the longest. So we'll treat this like a queue. We'll see the arrival time of 2 was the earliest arrival of all of our waiting processes. We pick P2 to run next. And now we see P2 get slotted in the running position, right? So what happens here is a scheduler dispatch, right? We'll call our dispatcher, which will change the currently running process. And the dispatcher will save P1 state as long as it didn't terminate, so that when it's done waiting, it can come back in and keep doing work. Anyway, so now we'll see P2 runs. We have no more processes arriving, so the next event we're going to see is going to be in 4 time units when P2 is done. So we'll see P2 here, which starts at time 7. It'll run for 4 units, right? So it'll be done here at time 11. P2 will be finished. So we can just see that goes on, and at time 11, P2's ran for 4 time units, right? So it ticked down all of its time. Great, so now P2's done. We'll look to our ready queue. Our scheduler gets called. First come, first serve is the algorithm we're using, right? So we'll pick out P3 because P3's been waiting the longest. So P3's up next. We see it take the running slot, and P3 only runs for 1. So we'll see it run from 11 to 12. Oh, and at time 12, we'll slot in P4, the only remaining process, which runs for 4 remaining time units. So we'll see it run from 12 when it starts to 16 when it's no longer any time to run. So this is how we schedule with first come, first serve, and how we use those tables. So the resulting Gantt chart or scheduling timeline, right? We see that P1 started at 0 and it ran for 7 time units. So at time 7, we transitioned from P1 to P2. P2 ran from 7 to 11. At time 11, we slotted in P3, which ran for 1 time unit, and finished at 12. 12 to 16, we ran P4. So this is our timeline, and we want to calculate some of our metrics. So the metrics, I guess, we'll calculate are mean turnaround time, mean waiting time, and throughput. The reason we calculate the means is because the individual turnaround time for a process doesn't actually tell us how well we did overall. So we'll calculate these metrics for all processes and then take an average. So here for our mean turnaround time, we calculate the turnaround time for each process. And as a reminder, this is our formula for turnaround time. If you're good at memorizing, perhaps you could just memorize this. For me, I prefer to think about what the metrics actually mean. So turnaround time, it means the time from it arriving to finishing, right? So how long from it arriving till it's done does it take for our scheduling algorithm to turn around and complete it? So for P1, right, it's arrives at 0 and finishes at 7, its turnaround time is 7, because that's how many time units it took. Likewise for P2, we see it arriving at time 2 and finishing at time 11, so it takes 9 time units and so on. We calculate these for all 4 processes to get these values, and we take the average to get a turnaround time of 8.75. Similar for wait time, right? Here's your formula for wait time. It's just the sum of the time in the ready queue. So the amount of time our scheduling algorithm tells the process it must wait before it gets scheduled. And the reason we might like wait time is that this is a more fair representation of how well our scheduler did, right? So our scheduler, it has no control over how long the process runs. So this is the turnaround time minus the burst time, minus whatever time it spends doing I/O. You can ignore this for our cases. We're probably not going to give you an I/O column, but hypothetically, if we were to say some statistical time it takes doing I/O before it comes back to the ready queue, you can subtract the I/O time too. It's just the time it's waiting in the ready queue. So here we calculate that for all of our processes. P1 obviously gets scheduled right away, so it doesn't wait. P2 arrives at time 2, but doesn't get scheduled again till 7. So that means it waited for 5 time units, right? It arrived here at 2 and waited till 7. That's a difference of 5. And you can do that for all the processes and take the average to get the mean wait time for this example. Great, and now the throughput actually here will be the same for all the processes, right? Because we're just going through these 4 and we're stopping when they're all done, right? But if we had a dynamic system, this wouldn't necessarily be the case. Throughput is just the number of processes per unit time. So how many did we get through per time? So if you're running this is something you might be interested in if you're doing like if you're paid by the job, for instance. It's how many jobs per second or something like that you get done. So 4 processes by 16 units of time is 0.25 processes per unit time. That's our throughput for this case. Not mentioned earlier, but was response time. So response time is the first scheduled time minus the arrival time. So it's saying how long did we wait before we got ran for the very first time. And for all non-preemptive algorithms, this will actually be the same as what we saw for the wait time. However, we'll start to see the response time change when we add preemption. So when we get to things like round robin, you'll see that maybe this starts going down because we're preempting and running them for the first time earlier. And the reason we care about response time is because this will mean some kind of visual progress for the user often, right? Some kind of doing work towards your goal. All right, so that's it for first come, first serve. Let's get into shortest job first. So here, shortest job first is going to say, well, maybe there was a problem with first come, first serve, right? Because if you had a big task that ran first, we're going to have really high wait times for all of our processes because they have to wait for that big, long process that got to go in first. So if we instead prioritize running our short jobs, we'll minimize our wait time. That's the idea behind this. And you can see it in the grocery store, right? If somebody has a lot of items in their cart, they're going to take a really long time to check out, so the line will get really long while everybody's waiting their turn. It can be avoided by instead prioritizing people with less items. Because they check out and get out of there quicker, you won't have a buildup of people in the line. So because of this, we'll see that shortest job first minimizes wait time because, or average wait time, I should say, because there'll be fewer processes waiting or fewer people in our grocery line waiting. And we can see this in actual grocery stores, right? You can see this in the express lines where they say if you have fewer than however many items, you can come to this special line where we'll get you out of here quicker, right? Because we don't want people waiting in the grocery store. That's a bad look. So we'll see 2 forms. We'll see preemptive versus non-preemptive. Your textbook, I think the newer version of the book refers to preemptive, shortest job first, and shortest remaining time first. So I'll kind of call them both preemptive SJF or SRTF. Great. So it minimizes wait time, but we'll see it's not fair, right? And if you're in a grocery store and you have a lot of items in your cart, you'll actually have to wait a very long time because everybody who's getting less items than you will cut in line ahead of you and get to check out first. And because of this time, you're going to wait for maybe people who arrived at the grocery store after you, but still somehow managed to check out before you. So this is definitely not fair, despite minimizing average wait time. Okay, great. So we're met with our exact same practice problem. So here we'll see at time 0, we've got P1 that's arrived. P1's arrived and it'll get scheduled straight away. Now we said that this is non-preemptive. That means when future processes arrive, they're not going to be able to interrupt P1. We can't pull P1 out of the running state back into the ready state. So what we'll find is that we have the same start. P1 runs all the way until it's done up here at 7. So all the processes are going to arrive and P1 is just going to keep running. And we get all the way to here. Because it's non-preemptive, nobody can interrupt it. So it gets to run until it's done. Now at the end of P1, something different happens, right? We look to our ready queue and we say, okay, what process do we run next? Last time we said, oh, well, we'll run P2, it's been waiting the longest. But this time we're changing our scheduling algorithm. We're saying shortest job gets to go first. So we can see here that P3 is actually our shortest job, right? It only has 1 CPU time. So we're going to sneak P3 in ahead of P2. And that's the one we pick next, right? It's got the shortest job, it goes next. It gets to run for its 1 time unit and we schedule between the remaining 2. Now here we've got a tie. I'm going to avoid putting ties in your exam questions if I can. Somehow I managed to put ties in every time. I don't know why, it just happens. If there's a tie, hopefully I've put a clause in the question to break the tie. If there is no tiebreaker, we'll accept all of the possible answers. So hypothetically, if there was no tiebreaker, you could pick either P2 or P4. But normally I'll put a tiebreaker and say something like, in the event of a tie, schedule with first come, first serve, in which case you would pick P2 to go first. That's kind of a reasonable thing you might do for fairness, right? The process that's been waiting the longest gets to go. That's more fair. Great, so in this case we picked P2. P2 is going to run for all of its time units. This is non-preemptive, so it goes for all 4. And then when it's done, we schedule P4, the final remaining process. So this timeline ended up looking rather similar. The only difference was that we snuck P3 in ahead of P2 because it had a shorter runtime, right? So P2 and P4, if we were in the grocery store, they both had the same number of items, so they just line up normal, but we sneak P3 in because they're only buying one thing. They're going to be quick. And the impact it has on our metrics is that it reduces the average wait time. Because last time we had P3 wait for 4 whole time units for P2, but P2 only has to wait 1 time unit for P3. So we ended up having less overall wait time by getting P3 out quicker. Even though it meant P2 had to wait a little bit longer, P3 would have had to wait much longer. So we're saving overall. And that's the main difference for metrics. Okay. So this time we're going to change up the rules. We're going to say, what if we let our processes preempt the running process? So we're enabling that interrupt in our scheduler. We're turning preemption on. So this will be preemptive shortest job first, or SRTF, shortest remaining time first. Great. Oh, a little bit ugly on the formatting, but hopefully you can look past that. So preemptive shortest job first, also known as shortest remaining time first here. So at time 0, P1 arrives, and it's our only process on the system, so it's going to get scheduled. Right, it gets scheduled, and it runs for 2 time units. Then P2 arrives. So now we've got a scheduling decision to make. Whenever you have a preemptive scheduling algorithm, it needs to get called every time something changes in your ready queue. Every time the ready processes are updated, there's potential to interrupt the running process. So we have to call our scheduler more frequently, we have to make our scheduling decisions more often, but we can maybe have a little bit better control. Okay, so we have something arrive, we have a preemptive scheduling algorithm, we're ready to make a scheduling decision. What we're going to do is we're going to check the shortest job first constraint and see, is the currently running process going to take longer than a process I have in my ready queue? And in this case, the answer to that question is yes, right? We see P1 has 5 units left, P2 only has 4. So we're going to run P2 instead. So we preempt P1, we put it back into the ready state, we do that interrupted arrow, and bring it back over here, and we run P2 instead. We'll see P2 runs until P3 arrives. Then we have a chance to make another scheduling decision. Should we preempt the running process in favor of running one of the ones in our ready queue? And much like last time, this case, the answer is yes, right? P2 still needs 2 time units, whereas P3 only needs 1. So we're going to switch the running process. We'll switch the running process in favor of running P3, so we preempt P2 and schedule P3 instead. So P3 runs, it takes its 1 time unit. We'll note that at time 5, we actually have P4 arrive, so it comes in here. Then we can schedule a new process, right? P3 is done, it's either waiting or terminated, it willingly leaves the running state, we get to pick a new process. The process we pick is going to be P2 purely because it has the least amount of time remaining. So P2 goes next, gets to go for its 2 time units, then we pick one of the 2 remaining processes, which will be P4, it needs less time. P4 runs for its 4 time units. It's now done at time 11. P1 gets to finish. So P1 runs all the way until 16. And this is our resulting timeline. So you'll note that we actually had a much more involved timeline, right? P1 started and then we interrupted it. We let P2 do some work and then we interrupted P2 in favor of running the short P3. Then we finished P2, ran P4, and then finally got to finish P1. We let P1 back in. So this would be like at the grocery store, if you were to stop checking out a customer have them pay and bring in a new customer if the new customer had less items than the existing customer. That sounds a bit ridiculous, but it's a good analogy for this, because the important thing that is easy to forget when you look at this timeline is that every time we change from one process to another, there's overhead, right? There's going to be this cost you have to pay in the operating system to transition from one process to another, right? You have to save P1 state and load P2 state. That takes time, much like P1 checking out, paying, and getting back in line. So it seems silly, right? It seems like a waste of time, but this waste of time also happens in your OS. So it's good to remember it, right? And then P2 gets halfway through checking out and P3 shows up with one item. So P2 has to pay and go back into the line and so forth. And what we find is that this one actually fully minimizes our wait time, because we never have a process waiting for one that's going to take longer than it. So we minimize this average wait time across all processes, despite having a little extra overhead. Cool. So that's preemptive shortest job first, and we can have kind of the summary as we get more aggressive about prioritizing the shorter processes, we lower our wait times. All right, so we're going to talk about round robin. Round robin is maybe a bit more about prioritizing fairness and response times rather than prioritizing minimization of wait time. So what we see here with round robin is we determine some time quantum Q. So we call this quantum Q the maximum amount of time that a process is allowed to run before another process gets a turn. So we set this hard upper limit on how long a process is allowed to run before we have to put it back in the waiting queue. And we call that the quantum. What we find is that this gives us an advantage. It gives us an advantage because it puts an upper bound on how long a process is going to be waiting before it gets to run. So if n is the number of processes on your system, right? Worst case scenario, they're already all the time competing for the CPU. And in that scenario, every process is going to get 1 over n of the available CPU time, right? In chunks of at most Q time units. That's just saying that, if you have 5 processes and they all want to run, they each get to run 1/5 of the time, and they get to run for at most Q time units. So here, if we're in the grocery store, right, this is like all of the customers wanting to check out all at once. They all only want to buy items, right? They want to buy unlimited items. They're each going to get a 1 over n amount of the cashier's time, and they're going to get to check out a maximum of Q items in a row, right? So that's kind of what we're saying. And because of that, right, the most amount of time you have to wait before seeing the CPU is going to be n minus 1 times Q. So if we have 4 customers who just want to buy items nonstop from our grocery store, right, and we say Q is 10, at most you can check out 10 items at once. The longest you're ever going to have to wait is for 30 items to be checked out before it's finally your turn again, right? That's the other 3 customers trying to check out items nonstop. They get to check out a maximum of 10 items at a time, so you'll have to wait for at most 30 checkouts before it's your time to run. Same idea here on our CPUs. Anyway, so we're going to see a trade-off in Q. That's one of the interesting parts when we study round robin is choosing Q. So if Q is large, then we have FIFO, right? If we say every customer gets to check out 1 million items, nobody's going to buy more than 1 million things at a grocery store. We might as well just have FIFO. However, if Q is really small, we're going to be constantly doing context switches. So if we say you're only allowed to buy 1 thing at a time and then you have to get back in line, it's going to be ridiculous at the checkout, right? Because you're going to have to constantly scan an item, pay, get back in line, scan an item, pay, get back in line, right? So if Q is too small, we're spending all of our time context switching and we're really not getting much work done, right? That would be a very inefficient grocery store. So that's kind of our thought behind this trade-off. All right, so let's get into it. It's not letting me go to the next slide here. All right, there we go. Let's get into round robin. So this time we're going to be doing round robin with a time quantum of 2. Note that these numbers are kind of small. The reason they're small is just to keep the example similar. And probably I have a race condition, judging by these tiny minuses that I put in the question. What I would be trying to indicate is that the arrival time here is 2 minus, whereas we'll say if your quantum expires, it expires at time 2 plus. So if we have a running process whose time quantum expires and a new process that arrives, we're going to say the new process gets to go first. Something that's updated here in our ready queue is we'll see we have this ordering queue and remaining time. So now we're keeping more close attention on the order of our processes because the order matters. It's no longer about arrival time, it's also about the order. Okay, so here at time 0 we have process 1, it's our only process. Our clock is 0 and we want to run P1. So P1 gets scheduled. Now the other thing to note is we have this time left in CPU. This is how long we have until our quantum expires. So P1 gets scheduled and initially we have this time at 2. And as the time ticks up, this time will tick down, much like our remaining time. And when we see that our timer left in CPU is 0, we're going to actually interrupt this process and bring them back to the ready queue. So we're interrupting this process and putting it back in the ready queue, and we say that P2 happened to arrive at 2 minus, so it arrived just before this date, right? We're prioritizing the new process over the process that's running. So we're going to put P1 back in the ready queue, and we're going to run P2 because its timer expired. Note that its remaining time is now 5 because we didn't forget we ran it for 2. And then over here we see we have P2. It's going to run for its 2 time units. So P2 runs for its 2 time units, and then at time 0 we're going to see that it gets interrupted and put back into the ready queue. Note because we have these little 4 minuses, we're saying that the arrivals happen before the preemption. So if the arrival happens before the preemption, P3 is going to be ahead of P2 in the queue. That's what I mean by this tiebreaker. So we'll see P2 goes behind P3, and then the thing we schedule is P1. And we schedule P1 because it's been in the queue the longest. Now, this is an important place to be very careful. It's very natural to say that P3 gets to go next here because it just arrived, it hasn't run, and your schedule will look really nice. It'll go in order, we'll say 1, 2, 3, and we like to count. This is a common error that students make when they're trying to rush these questions on their exams. It's important, especially for round robin, but important in general, to keep track of the order of your ready queue, right? So note that P1's been in the ready queue the longest. It joined the ready queue at time 2. So P2 and P3 are both behind it, and we said this ordering was because of the minus here. Okay, so we schedule P1. It's been in the longest. P1 gets to go next. While P1 is running, we see P4 arrives. P4 arrives here at time 5. We'll put it at the back of our ready queue. So now what we're going to see is these processes cycle in the order of 1, 3, 2, 4. And it's not natural because that's not the order we count. We get that order by maintaining the ready queue. Can't stress that enough. Anyway, so P1 gets to go until its time quantum. It exhausts its time quantum at time 6. It'll go back into the ready queue. We'll put it at the tail end of our ready queue. Then we get to run P3. So P3 gets to go next. P3 is slotted in. P3 runs for 1 time unit, and we see that it has no more time in its CPU burst. It's done doing whatever it was trying to do. It's going to leave our scheduling for this question. So then we'll take in our next process, which is P2. P2 is going to run for its 2 time units, and it's all done. Right? It leaves our system. So we'll take P4. P4 goes for 2, exhausts its time quantum, so it gets interrupted, put back in the ready queue, and then we'll slot in P1 to go next. P1 uses its quantum back to P4. P4 finishes altogether, so it's done on the system, and then P1 gets to run. So we end up with this much more complex timeline, or maybe not more complex, but the idea here is that it has a lot more transitions, right? A lot more transitions back and forth between the processes, increasing the number of context switches, causing more overhead. So in these questions, we don't add time for context switching, but remember this is like our cashier going to check out P1 P1 pays, gets back in line, P2 goes, P2 pays, gets back in line, and so on, right? So there's a lot of extra overhead with this. All right, we calculate the average response time. We'll find that this typically has the best response time overall. I think when we compared this to the preemptive shortest job first, just by the nature of the question, the preemptive shortest job first actually had a shorter response time with all these preemptions that happened. But in general, we'll see that this prioritizes average response time. Great, we talked about this kind of extensively in class, so I'll just skip over this talk about the quantum and the comparisons. But the last scheduling algorithm I just wanted to mention and go through the slides nice and thoroughly is this priority scheduling. So for priority scheduling, we have two types. We can have preemptive priority or non-preemptive priority. In this deck, we're only going to go through the preemptive priority example. The reason for that is preemptive priority is much more common than non-preemptive. So we'll do preemptive priority, and it's worth noting that shortest job first. We already learned it. It's an example of our priority scheduling algorithm, right? Shortest job first just prioritizes short jobs. So we say our priority is, instead of being some arbitrary integer decided by the person configuring our system, it's going to just be the predicted CPU bursts, right? And with the shorter bursts meaning higher priority. Now, typically the priority number is going to be an integer, and the low priority values are going to be considered as higher priorities. I didn't come up with this standard, and it's maybe not always true, but in general that's the case. We'll specify this whether high or low means good or bad in your question if you're given a priority scheduling question. Okay, great. And then, of course, whenever we have some kind of priority, right, you have to consider starvation and aging. We addressed aging with the multi-level feedback queues. Okay, let's get into preemptive priority. So here, what we've done is we've added a new column to our table. This column gives every process a priority number. We're going to be using the low priority number means it gets to go first. So it has higher priority, right? So the lower integer means that it actually gets to go first. We'll keep track of their priorities when we're running and build out our schedule here. And although I can't remember, maybe we calculate the metrics at the end, right? The metrics don't matter as much as the priorities. Whoever configured this system decided that P2 is the most important, and we don't really care about the impact on the metrics. It gets to go first, right? This could be some kind of real-time system where maybe it's safety critical and P2 gets to control the airbag in our car, right? I don't care about how long it takes or when it arrived. If the airbag wants to deploy, we deploy it first. Where 3 might be our infotainment system. I don't care if we're queuing up the next song when I want the airbag deployed. Something like this. All right, so preemptive priority. At the start, P1's our only process. It gets to run till time 2. Nothing changes there. We'll see P2 arrives. P2's got a priority of 0, so we're going to preempt P1, right? This is preemptive priority. We say, P1, get out of here. We have something very important to do. So P2 gets to run. It's going to run till time 6. This is the highest priority. Nobody's going to interrupt, right? So we see all the other processes arrive, but nobody gets to interrupt P2. P2 goes till it's done. When P2 is done, we're going to pick a new process. We're going to pick a new process based on their priorities. So we'll look at this list and find P4 has the most important priority number. P4 will get to go next. P4 runs for all 4 of its time units. No new processes are arriving, so nobody's going to preempt it. At time 0, at no time remaining for P4, we interrupt it, or we terminate it, or bring it to waiting, right? When we do that, we're going to look at our ready processes. We'll find P1 here is the highest priority. We'll bring P1 in to finish running. When P1 finishes, we'll bring in P3. P3 will get to run for its 1 time unit, then it's done. We get a timeline like this. Non-preemptive priority is available in the speaker's notes for your slide decks presented in class if you wanted to try that one on your own. Really, the only difference is that you don't have this interruption here at time 2. Instead, P1 gets to go for its full 7 units, right? Non-preemptive means we can't interrupt it. So at time 7 here, we'll just do P2, P4, P1 in that order because of their priorities. That's how the non-preemptive timeline would look.